All right, this is lesson 26, example problem 4. So we have a beam supported by a roller at point A, a pin at point B. It has a 6 kilonewton downward force on the left side, an 8 kilonewton downward force kind of in the middle right, and then a 6 kilonewton meter applied moment. So an applied moment is a concept we haven't covered in this class so far. Really, it's similar to an applied force, except it's a moment. So if you're doing some of the forces calculations, like some of the forces in the x direction or some of the forces in the y direction, it isn't part of those equations because it's a moment, not a force. When you do your sum of your moment equations, right, which we would sometimes write as sum of d times f, well, it's going to pop into that because it's a moment. However, you're not going to have to do any distance times force because it's already in Newton meters. It is already a force times a distance. So you'll see how this plays out as we solve for the reaction forces in this problem. So it asks us to solve for the reaction forces and then graph the shear and moment diagrams, just like in problem examples 1, 2, and 3. So we'll go ahead and get started the same way we always do. So if we have a roller support at A, that means we have an AY at that support. And if we have a pin support at B, that means we have a BY and then also a BX. So if we do sum of the forces in the x direction is equal to 0, the only force in the x direction is Bx. Therefore, Bx is equal to 0. So that wasn't too bad. If we do sum of the forces in the y direction is equal to 0, starting from the left, we have a negative 6 kilonewton force. Then we have a positive AY. Then we have a negative 8 kilonewton force. And then we have a positive BY. And again, the 6 kilonewton meters is an applied moment, not a force, so it doesn't factor into our force equations. So then when we do our sum of the moment equations, let's define counterclockwise as the positive direction of rotation. So we'll just, we're going to sum the moments around point B. All right, so we're going to sum the moments around point B. So our 6 kilonewton force is 8 meters to the left of point B, and it would cause a counterclockwise rotation. Therefore, it is 6 kilonewtons times 8 meters. And it's positive because it's counterclockwise. So then we have our AY, which is 4 meters away, but it would cause a clockwise rotation. So, right, because that would go like that, that would go like that, that would go like that. So our AY is going to be negative, so AY times 4 meters. Next we have our 8 kilonewton force, which is again counterclockwise rotation. So plus 8 kilonewtons times 2 meters. And then we have our 6 kilonewton meter moment. So it is already a moment. It doesn't need to be multiplied by a distance, and it's clockwise. So that's going to be minus 6 kilonewton meters. And then By is at the point of rotation, so it's going to be multiplied by a distance of 0. All right, so that one doesn't come into this. I guess if you technically want to write it, we can go a little more off to the right here and say plus By times 0 meters. Hey, that's 0. Okay, so if we solve through in our moment equation, we can get that Ay is equal to 14.5 kilonewtons. Okay, if we have 14.5 kilonewtons, we go back to our sum of the forces in the y direction. We have negative 14 kilonewtons, that's the 6 and the 8 combined, plus 14.5 kilonewtons, plus By is equal to 0. That gives us that By is equal to negative 0.5 kilonewtons. Okay, so this is the first time we've gotten a reaction force that's a negative number. So what does that mean? Well, B is a pin support, right? It kind of looks like, if you were to look at it in real life, some kind of hinge looking thing with a pin running through the middle that then connects to the beam kind of going around it like that. So the pin doesn't always provide a force in the upward direction on Y. It could provide a downward force as well. If someone were trying to lift the beam up, the pin would keep you from lifting it. So that's kind of the situation we're in right now is the pin is actually holding the beam from being lifted up around up above that pin, which is fine. It means that the direction we drew by on by isn't perfectly accurate, but that's fine. It just comes out as a negative number. Everything is fine. So we have our supporting forces or our reaction forces. So the next step is to draw our shear and moment diagrams. So I'm going to drop down a little bit and I'm going to redraw our picture with all of our forces on it. So we got that. We got an upward force at A. We got our downward 8 kilonewton force. And then since By came out as a negative number, when we drew it as an upward force, that really means it's a downward force. So I'm just going to draw it the way it actually is right now. So this is 6 kilonewtons. This is 14 kilonewtons. This is 8 kilonewtons. And this is 0.5 kilonewtons. And then just as a reminder, I'm going to draw our little moment there as well. And we'll come back to how that ends up getting used. Okay, so shear diagram. We draw our shear. We draw our x-axis, which is going to be in meters. Our shear is going to be in kilonewtons. All right, so we start at 0. Our first force is a downward 6 kilonewtons, so we drop down to -6 on our shear, and then we go straight across. And then we have an upward 14, so -6 plus, sorry, that's 14.5. I'll fix that. So that is an upward 14.5 kilonewtons. Okay, so -6 plus 14.5 is positive 8.5. So we go all the way up to positive 8.5. And then we go over. And then we have a downward 8. So 8.5 minus 8 brings us down to 0.5 kilonewtons. Then we go across, get to negative 0.5. 0.5 minus 0.5 gets us back down to 0, which is good. That's what we wanted, right? You always have to start and end at 0 on shear. So this is at 4 meters, this is at 6 meters, and this is at 8 meters. Okay, so our shear starts and ends at 0. We're good to go. And again, notice we didn't use our applied moment when we were doing our shear diagram because we don't have to. Shear, you just look at the forces. So next, we're going to do our moment diagram. So I already know what the answer looks like. That's why I'm going to draw this as having a very big negative portion. And you'll see why in a minute. So x is going to be in meters. Our moment is going to be in kilonewton meters. Okay, so we have our first area. It's 4 meters across. It's -6 meters high. 6 times 4 is -24 kilonewton meters, right? Remember, integral of shear is equal to the moment. So to do that integral, we're just going to do the area of all these different boxes. So our first box is -24 kilonewton meters. The next one is 2 across by 8.5 tall. 2 times 8.5 gives us 17 kilonewton meters. And then our last one is 2 across, 0.5 tall, gives us 1 kilonewton meter. Okay, so we're going to start at 0, 0. By the time we get out to 4, we have to have gone all the way down to -24 kilonewton meters. So that's at 4. Connect those lines. Okay, between 4 and 6, we go up by 17 kilonewton meters. 24 plus 17, or -24 plus 17 is -7. So we're going to end up right there. So then connect those dots. And then we go up by, add 1 more kilonewton meter between 6 and 8. So we go up to -6. So then, now we have to take that applied moment into account, right? Because when we get to 8, that's where we have another 6 kilonewton meters. And that's what's going to get us from -6, get us back up to the x-axis. Now we have our moment diagram starting and ending at 0 the way it should. So things we learned in this problem that are different. So applied moments. They do not affect your sum of the forces in the x direction or your sum of the forces in the y direction equation. However, when you do sum of the moment equations, they do matter. So you do have to bring them into there. When we do our shear diagram, they don't matter. When we do our moment diagram, they do matter, right? So you got to make sure you take them into account when you're doing sum of the moment equations and when you're doing your moment diagrams. The only other big thing to look out for when you're doing applied moments is just make sure you get the direction right. They'll usually have a direction drawn on them, and whatever direction you choose to be positive is going to affect whether that applied moment is positive or negative in your sum of the moment equations. All right, and that's really all there is to them. They're not super complicated, but it is something new. So try this problem on your own. See if you can get through to the right answer. Okay, thanks.